Okay, so the best thing to do for this problem is to set up a picture where you can see what's going on. A singly charged ion, when they say singly charged, that just means the charge of a proton. The way atoms become charged is either by gaining electrons or losing electrons. So, if you have a situation where there's one more proton than there are electrons, that would be singly charged. And the net charge of that ion would be the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs. And then we have the mass of this charge. Okay, and it's accelerated through a potential difference of 250 volts. So where would you find a potential difference of 250 volts? A great way to think about it is oppositely charged parallel plates. So I have this diagram right here where the positive charge is being released from the positive plate, and what's going to happen is, so these arrows here represent the electric field. Positive charges want to move with the electric field, so this positive charge is going to be accelerated through here, and I put a little gap between the negative plates. So then the charge is going to go from here, it's going to go between these negative plates, and it's going to be launched into region 2, which is only magnetic field. And the thing they want us to find is the radius of the circular path in the magnetic field. So we've already talked about in class how if you have a charge that moves perpendicular to a magnetic field, it's going to follow a circular path because the net force on the charge, no matter where you look at the charge, if you do right-hand rule number 1, you're going to find, like if the velocity is that way, apply the right-hand rule, you're going to find that the force points that way, right? When the charge is right here, the velocity is that way, which means the force is going to be that way, right? So the force is always to the center of the circle. So anyway, the first thing we have to do is find the velocity of the charge as it leaves region 1, right? And then we can assume that the initial velocity is 0. The charge starts from rest. Let's see, do they say that? I don't think they specify it, but we have to assume it. Okay, so starting from rest, if this charge is accelerated through 250 volts, how do we go about finding the velocity? Well, look, the way you do it is it has to do with the definition of potential difference. So this V here is voltage, not velocity. What's the basic definition for voltage? It's change in potential energy per charge. Now look, as this charge is accelerated down the electric field, is it losing potential energy? Yeah, but what is it simultaneously gaining? Kinetic. It's just like if you take a mass and drop it. If I hold up a brick, if I drop a brick and the brick accelerates down the gravitational field, the brick would be losing potential but gaining kinetic. So what we can do is we can go, all right, this is going to be equal to the change of kinetic as well, right? That's all that is conservation of energy. So I'm kind of short on time here. So change of kinetic is going to be kinetic final minus kinetic initial over the charge. But if the charge starts from rest, what's kinetic initial? 0. So now what we do is we plug in for kinetic energy. This is going to be 1/2 mv squared over q. Hey, don't confuse those v's. This v here is voltage. The second v is velocity. So what we're going to solve for is velocity. I'm short on time, dude. The bell's going to ring, so I'm just going to tell you the answer. So velocity comes out as 56,568.5, and then we go on to part 2. So let me erase this. So that's our velocity. So now we go to region 2. In my lecture, the equation, when a charged particle is traveling perpendicular to a magnetic field, the equation is mv over qb. So look, take your m, plug it in. The v we just solved for, what was it, 56,568? Plug that in, we got the Q, and then, I erased the B. The B was 0.5. Plug that in there. You plug the numbers in, it comes out as 0.0177 meters, which is 1.77 centimeters.